Okay, so today we're going to sort of head back into what we were doing before, the deformation theorem and sort of consequences of the deformation theorem. So let me just put up something that we could have observed early on, which is that, so you remember back, kind of early on in the book, we did this theorem where we showed that every holomorphic function in a disk had an antiderivative, right? Do you remember that? And we did that right after Cauchy-Grassat. And the way that we did it was that we basically if you recall, what we did was so you started off with this function that was holomorphic. And then you defined another function, which was just you fixed some point in the disk, I guess the origin, the center of the disk, z0. And then you created a path, gamma z, going from z0 to that z, right? And I guess in that case, the path that we had was like this, right? And then we played that game of, if you have some z plus h, then the difference f of z plus h minus f of z, you got by just integrating over this line segment, right? And then by reason of continuity, you saw that the difference quotient would converge to f. That is, that this guy was the antiderivative. You guys remember that? At least roughly, you believe what I'm saying here. All right. So this is how he did it. So what was important was if you think about it, okay, then actually. We could have made a more general theorem at that point, something that we will use a few times. We've used this sort of fact a couple of times, and we're going to use it a couple of times today. We could have made a general theorem at that point, which is the following. So if you have a function which is continuous on some region omega, then the following are equivalent. One, f has an antiderivative. On omega. Two, any contour integral in D, in omega of f is path independent. In other words, dependent only on the endpoints. And three, any contour integral over a closed curve is 0. Okay, so this is it's just something simple that we could have noted early on. Okay, right, like whenever you have an antiderivative, right? If you have an antiderivative, then it's true that any contour integral of f is going to be path independent. Right? This is just the fundamental theorem of calculus, basically, right? And then so 1 implies 2 is fundamental theorem of calculus. The equivalence of 2 and 3, I hope is obvious, right? Right, like if it doesn't matter, right? If integrals over different paths give you the same value, well, integral over a closed curve is going to be 0, right? Because the value going this way and the value going this way are going to be negatives of each other, right? So the integral over a closed curve is 0, and conversely, if the integral over a closed curve is 0, then the integrals over paths are going to be the same, right? Because if you have a curve, then the integral over this is 0. So the integral over these paths are the same, right? So 2 and 3 are being equivalent are trivial, are obvious, right? Right, and then 2 implies 1 basically follows in exactly the same way that we did in that earlier proof. Okay, right. So what you do, so 2 implies 1, right? That's this business. If you have path independence, then you just generate. You say, well, let f of z be this. Fix some point, some z naught in your domain, and then define this contour integral guy, where gamma z is just any path going from z naught to z, right? And then you play exactly the same game. You say, well, look, f of z plus h minus f of z is going to be the integral of f over the line segment from z to z plus h. Right, where your h is small enough that there is such a line segment. Okay, right. So h for some small h, right? And then you say, well, look, your function your function is continuous, so you can write f of w. So let's call this f of w dw. You can write f of w as f of z plus some error, right? Plus some error that the limit of this error is 0 as w goes to z, right? Just by continuity, right? Just by continuity, right? And then you say, okay, well then, this thing is just going to be the integral over that line segment of this thing, right? But this being constant, you can pull that out, and so you end up with f of z times h, and you get this other thing, right? Right. But this thing is controlled by, the size of this is controlled by the supremum on the line segment, times the length of the line segment, right? And then when you take the difference quotient, right, you divide this thing by h, and you end up with this thing as h goes to 0, this thing vanishes, and then this thing is just f of z, right? So I'm just sketching out. You know this proof already. You've seen it before, right? So it's exactly the same proof as what we used in that early theorem, right? So so 2 implies 1. Okay, so these things are equivalent. Okay, so anyway, okay. So now let's get back to the definition theorem. Just a second. Sorry, it's just shutting down. Okay, so now let's get back to the definition theorem. Yeah, oddly, the last time I did that in another class, and the students were like, you can just go to the door and close it, rather than going in this circular path. But yeah, anyway. Okay, sorry. So recall the defamation theorem. So now we're going to talk about simple connectedness. Simple connectedness. so let's recall the deformation theorem. So what does the deformation theorem say, right? If you have a function that's holomorphic, and you have two curves, gamma naught and gamma 1 are curves that are homotopic. In omega, then the integral over gamma naught and the integral over gamma 1 are the same. Okay. So, yeah, in other words, as long as these curves are homotopic, yeah, so, yeah, exactly. Okay, so that sort of prompts the following definition. Let omega be a region if all curves with the same endpoints are homotopic, then we call gamma simply connected. Okay. If all curves with the same endpoints are homotopic, then we call gammas simply connected, right? So this is saying that you're in such a region that whenever you've got two curves that have the same endpoints, then you can deform one guy to the other guy, right? So this is the mathematical way of saying that your region has no holes, right? You can right. So like if we were on the complex plane, the complex plane is simply connected. But if I take the complex plane minus the origin, then it's not simply connected, right? Because I can certainly some paths are with same endpoints are like this guy and this guy have the same endpoints and they're homotopic, but this guy and this guy have the same paths and are not homotopic. You get caught on this hole here, right? You can't deform one continuously to the other. Okay. So right. So you see the connection between what we were saying before, right? So if all curves that have the same endpoints are homotopic, then the deformation theorem says that that all integrals are path independent, right? Right. So right. So if this is simply connected, and f is holomorphic, right? Then then any pair of curves with the same endpoints are homotopik, and so right, and so the right, and so the integrals can be the same, right? So so then all contour integrals of f are path independent, right? And so by the previous theorem, you're guaranteed the existence of primitives, right? So this is antiderivatives. Right. So this is just to extend it to, we have this sort of thing for simple for like disk and stuff, and this is just extending it to the case of simply connected regions. Okay, so when does a holomorphic function have a primitive? Well, if the region is simply connected, then you're guaranteed it. Okay. So Stein goes from here to talk about the complex logarithm. I'm going to present the complex logarithm in a slightly different, I'll do it in two ways. One way which I think is maybe more elementary, and then Stein's way. Okay, and they're roughly this. They are effectively the same way, but I think maybe one way is a little bit easier to think about. Okay. So complex logarithm. Okay. Okay. So let's recall how we defined e to the z, right? So z was, where z is some complex number x plus iy, right? We define this as e to the x times e to the iy, right? And in turn, we define e to the iy as cosine y plus I sine y, right? That's how we started off defining the exponential function, right? This is actually like kind of a not the way you want to do it, to be honest. This was sort of like a stopgap way of defining the exponential function, right? So, right, yeah. So really the way you want to do it is to use power series. So you say, look. You can take the power series. This is just a side comment, right? You can take the power series for this, and then you can extend it to a power series for complex variables, right? And that power series is valid on the entire plane. And you do the same thing for cosine and sine, and then you see that then you see that this relation holds true. Okay, but anyway, so we defined the exponential function in this kind of funny way to start off with. Let me just remind you of the term the argument, right? Right, so the argument of a point means just means the angle, right? So so if you have some point here, then this is the argument, right? This angle is the argument, and we generally you think of argument as something that can range from negative infinity to positive infinity. Right, so each point has an infinite number of possible arguments, right? So there are infinitely many arguments for the same point. One term that I haven't mentioned before, but I'll mention it now. If I say argument with a capital letter, I mean that it's the argument that goes between negative pi and pi. Okay, so like just between negative pi and pi, we'll call that the principal argument. Right. So the argument of any point, of course, is going to be the principal argument, plus 2 pi integer multiples of 2 pi. Okay. So yeah, just that's one thing. Another thing. Just like some simple observations, so trivial observation. E to z equals 1 if and only if z is 2 n pi I for some n in z. right, if you're on the plane and you know, e to the z equals 1, well, right, e to the x plus iy, that tells you that e to the x plus iy is size 1, right? But you know, this iy doesn't have any, you know, e to the you know, this iy doesn't affect the size of it, right? It just rotates it, right? It just rotates the number, and so you know that e to the x equals 1, right? Which tells you that x must be 0. I mean, x must be 0, right? So x must be 0, right? So e equals x plus iy. X is 0, right? And you know, you have to be, you know, you have to have an angle of 0, and so you know, you must be some integral multiple of 2 pi, right? To be at this end, to have this argument. Right? Okay, so just a trivial observation. Okay, that's one trivial observation. Okay, another is the following, that one can obtain any non-zero point w being a plus ib by choosing, of course, z equals x plus iy, where e to the x is the size of w, is the magnitude of w, and y is the argument of w. Right? I'm not saying anything fancy. Right? All I'm saying is that, look, if you have some point w, we can get that as e to the z for some z. Right? How do you do it? You say, well, look, I choose, you know, I choose my x so that e to the x is the magnitude of w, right? And then I choose the right angle. I choose the correct angle, right? I choose argument of w as my y, right? And that will give me, you know, then e to the z will be that w, right? Right. So what's the point here? That e to the z maps onto, so it maps, you know, the complex plane onto the complex plane excluding 0. Right. Right. And of course, as you you know, if you right, so I would need to choose my x to be, I choose my x to be the magnitude of w, and I would choose my y to be the argument, you know, wherever that is. So argument of w. Right, or maybe I'll say make it the principal argument of w. Right, so this point is going to get mapped by e to the z to that w, of course. Right, and right, if you go up by 2 pi, right? So if you go up by 2 pi, then you end up at the same point again, right? Because going up by 2 pi just makes you spin around, just makes e to the z spin around and come back to here, right? So e to the z is 2 pi I periodic, right? So right, there's in fact infinitely many points that will get mapped to w. Right? It's not just, you know, it's not just onto, it's infinite to 1. Right? So notice that e to the z is 2 pi I periodic, and right? They're infinitely, yeah, it's 2 pi I periodic. Okay. And so what's the point of this last comment? The point is that if I take any strip, if I take any half-open strip, right, of height 2 pi, then that maps onto in a one-to-one manner onto C excluding the origin, right? So each one of these half-open strips, is e to the z is one-to-one from any of those half-open strips onto C excluding the origin, right? Right. So let me put down some notation. Okay. So some notation. For any y naught in R, let a naught, a sub y naught denote the strip x plus iy, where y is bigger than or equal to y naught and less than y naught plus 2 pi. So this is the half-open strip. This is just the half-open strip starting at y naught and going up 2 pi. So this is the horizontal strip. Okay.
Is that an A or?
That's an A, sorry. It could be an F or I'm not sure what that is. Yes. It is an A. Okay. Yeah. So observe that for any one of these strips, e to the z is 1-to-1. Is a one-to-one map. Is a one-to-one map of the strip onto C excluding 0. Okay. Why? Why? Well, the only if 2 points end up in the same. So suppose like ez naught equals ez1, right? But in that case, e to the z naught minus z1 is 1, right? But we saw earlier that the only things that give us 1 must differ by integral multiples of 2 pi, 2 pi I, right? So right. So these guys must differ by 2 pi I, but the height of the strip is 2 pi I, right? So you can't have, they must be the same. They must be the same plane. Right. Since z naught minus z1 must be 2 pi I n, right, for some n in the integers, right? And since they're both in the strip of height 2 pi I, well, they must be the same point. N must be 0. So just a bunch of simple observations so far. Okay. Okay, everybody all right? Okay, so what's the point here? So, okay, so now let's talk about the logarithm. Okay, so right, so e of course is an infinite to one function. So you can't normally talk about an inverse function, right? You want log to be an inverse function, but e is an infinite to one function, right? So, of course, what we're going to do is we're going to restrict, right? We're going to restrict the image. Okay. So the image of the inverse function, right? Or the domain of E. Okay. So let me, and this this part is sort of not following the way Stein does it, but we're gonna do it both ways, and just make sure that we keep our head straight. Okay. So given any w in C excluding 0, we say w is a logarithm of z. If e to the w equals z. And we write log w equals z. I'm sorry, w equals log z. W equals log z. Okay, so there's going to be infinitely many logs. Okay, for each z, there's going to be infinitely many logs. Okay, so in order to make this a reasonable, like a one-valued function, a single-valued function, we do the obvious, and we say, well, so we call the function log from C excluding 0 to the horizontal strip at height y0, going from z to natural log z plus I theta, where theta lies between y0 and y0 plus 2 pi. So we call that the branch of the logarithm lying in a y0. Okay, so so what's the point, right? That remember, if you have some y0, and right, we know that if we look at e to the z restricted to it, well, that's a one-to-one onto map onto this plane, and so we take the branch of the logarithm lying in y0 is just the inverse of that function, right? Of that function whose domain has been restricted. Okay. Okay. So just a remark. One sometimes calls if y0 is negative pi, we call this the principal branch. Of the logarithm. Okay, and I'll denote that as capital log. Okay. If I ever write natural log, ln, I mean just our old real valued function natural log. Okay. So this means old log. so right, so in particular, so just so notice that the principal log is going to be natural log plus I times the principal argument, right? Because the principal argument was the one that's between negative pi and pi. Okay, so right. So for example, right, if we take some, so suppose we take some point, suppose we take some point on the negative real axis here. Okay, right. That's gonna, that's going to be. So that would start off, so if I'm looking at the principal branch of the log, so here's my graph, right? And this is negative pi, and this is pi up here, right? This is going to start off, this is going to be, have a negative, it's going to start off with some, some argument of negative pi, right? And then if we walk around the circle like this, right? We walk around the circle like this, then those points, log will map those points like this, right? Because the right the modulus doesn't change, only the angle changes, right? Right. So so this point gets mapped to here, and as you walk around like this, then you're walking up this line up to here, right? Okay. So, and when you come back to here, you notice that you don't have the same value at all, right? Your function is actually discontinuous, right? So. Right, when you come back to this point from the top, or if we were standing at that point and then moved upwards from there, right? If we were standing at that point here, right? His output is here, and moved upwards, the value would jump, right? So if we wanted yeah. So this function becomes discontinuous at this negative real axis. Everybody see that? Everybody see that? Right. So the function is discontinuous at the negative real axis. Right. So the what people do as a solution for this is to introduce the notion of a Riemann surface. And I'm just going to touch on this informally. So what you do is you say, well, right, in order to make this continuous, I'm going to think of taking another copy of, so you take one copy of the plane like this, and you take another copy, and you say, well, when I come around to here, then I'm going to switch branches, right? I'm going to switch from this branch to the next branch up. Okay, I switch to the next branch up, and that way I can make a continuous function, right? So like when I come here, I'm not going to say that I come back to this plane. I'm going to say that I go to the next plane. Okay, I go to the next plane and go like this. And when I come here, I want to switch to the next branch, and so on and so forth. So the natural domain of the logarithm function is an infinite number of sheets, copies of the complex plane, sliced and glued together in this way, right? So you have this feeling of like when you pass through here, then you end up here. When you pass through here, you end up here, and so on and so forth, right? So and that will give you a one-to-one function, right? That will give you a one-to-one function from no, what am I saying? Yes, that's right. That will give you a one-to-one function from this Riemann surface to the complex plane, right? Or if you want to think of it, it's an infinitely valued, well, no, the other way is infinitely valued, sorry. That will give you a one-to-one function from the Riemann surface to the complex plane. Okay.
Different points on the Riemann surface mapped to the same point on the complex.
No, because they get mapped to different strips. Right? Each copy gets mapped to one strip.
Oh, under the, yeah.
For log.
Yeah.
For log. So this one would get mapped to this the principal strip. The next one gets mapped to the next one up, and so on and so forth. Okay. When we get to it shortly, when we define square roots, you'll see that it will be a two-valued function on just a two-sheeted Riemann surface. So when you cross here, you come to here, and when you cross through it again, you come back to the original surface. Those of you, some of you may know that this was the inspiration for Alice in Wonderland, or Alice Through the Looking Glass. That the author was a mathematician, right? Charles Dodgson was a mathematician, and he thought, oh, this is a cool idea. I'll use this in a story, right? This is the looking glass. Alice passes through the looking glass and ends up in this world where everything is backwards, right? These are where the negative square roots are, right? These are the negative square roots. These are the positive square roots. Everything is backwards in this weirdo world, and she has to pass back through the world to return to the normal world. Right? Okay, but we'll see that. We'll see that shortly. Yeah, we can actually do that properly. Okay, so now I'm going to do Stein's way of doing things, which has its advantages, but I think it's easier to think about if you have this in the background, in your mind. Okay, so Stein's presentation. So Stein says, let omega be a simply connected set region, say, yes, containing one but not zero. Okay, so you've got this. It contains one but not zero. And you see that it's simply connected, so you're never going to you can never make a loop around. You never can make a loop around the origin. Okay, it's got to be simply connected. Okay, so something like this is not allowed. Okay, right. Okay, so he says, well, let's define. We define the log of omega, the log on omega as just by taking the integral of 1 over w dw gamma z, where gamma is so gamma z is any curve from 1 to z. Okay, so you have some point z, and you take any curve to that point, and you integrate 1 over w to there, and you call that the log. Okay, and that's well defined, right? Because we're simply connected, and it doesn't matter what path we take by the deformation theorem. That's why we needed the deformation theorem. Okay. So, as usual, a bunch of trivial comments. When I first started teaching, the professors who were watching me said, "Stop saying trivial so much," and I see that I've fallen back into it after 30 years, 33 years, 32 years. Okay. Okay. So it is easy to see. It is easy to see. Yeah. You see, I'm kind of betrayed by my notes because it's like it is trivial to see. It is also trivial to see. It is easy to see that that there exists an interval 1 minus delta, 1 plus delta, contained in R. So, right, that we can, in which log, this log equals our old log. Right, because, right, if, you say, well, look, this omega is omega is open, so we know that we can find some open interval around 1 that's contained in omega, right? And then, log is defined in this way, but we can take, if R, so for R in that open neighborhood, right? So if you have R here, you're allowed to take any path, right? So let's just take the line segment, and then we've got our old definition of the log, right? The old definition of log is just integrate on the line segment from 1 to R, 1 over x dx, right? And so, since we're allowed to take any path, let's just take that one, and so, this integral is clearly that integral. They're the same. Okay, so what does that tell us? That this agrees with the logarithm, or with our old logarithm. In other words, it's going to be an extension, a holomorphic extension of the real logarithm to omega. Okay, so so second comment is that it's also easy to see that that this function is holomorphic. Okay, why? Because the integrals are path. It's basically the same argument as before, right? So. No, because why? Because 1 over w is holomorphic in this simply connected region. Right, and so from what we said before, right? If you're holomorphic in a simply connected region, then you have an antiderivative, right? Right, and this is the antiderivative, right? This is the antiderivative. You can differentiate it and get back to here. Yes?
Doesn't it just follow from the fact that Why do we need 1 over W to be holomorphic?
Just to use the previous.
Because it's the integral of some function. And isn't that enough to say that that function is its derivative?
Yeah. So, or just continuous.
Isn't it just enough that the integral is well defined?
Well, what if the integral wasn't differentiable? Then you should be able to take 2 derivatives of it. Like once differentiable implies.
I think the fact is integral would require just by the time.
No.
Okay.
Let's talk after. I don't think so. I don't think so. Yeah, let's talk after. That's what I should say more quickly. Almost invariably, I have these long pauses in the videos that are like me just standing there. I should just say, we'll talk later. Okay, so yeah. So in any case, this function is holomorphic, right? And then so when you take when you create the contour integral of it, that contour integral is the antiderivative of this, and so this is differentiable. Okay. Third comment. So why is this thing actually an inverse? For all z in omega. So one way of saying it is this kind of unsatisfactory, but fine way of saying. You say, well, look, it suffices to show that z times e to the negative log omega is constant, constantly equal to 1. And then we play the game that we played before. You differentiate it, and you see that that this thing has a derivative of 0, and then you evaluate it at 1, and you see that that the value is 1 there. Okay. So differentiate. See that the derivative is constantly equal to 0, and evaluate as z equals 1. And so the value is 1 at a point, and it doesn't change anywhere else. So it's 1 everywhere. I'm not gonna do it. Okay. So right. So this actually does create an inverse function for the exponential function. Okay, and then Stein's way of giving the principal branch of the logarithm, which is equivalent, is to say, well, now let's take omega to be c excluding the negative real axis. Okay. And then we're going to call the principal branch log omega, using that omega. Okay. So we take, our omega is going to be the complex plane, but excluding 0 and the negative reals. Right. Right. And then we're going to so then log this log omega will be the principal branch of the logarithm. Okay, and the way to see that this is the same thing is to say, well, look, if I have some point z, then let's take, remember, we're allowed to take this over any, this thing is going to be the integral of 1 over w over any curve that goes to z from 1, right? And so the curve that we're going to take is this one, right? So we go from 1 to the absolute value of z, right? And that is, what's that going to give us? That's going to give us natural log of the absolute value of z, right? That part will give us this, right? And then we integrate over this circular path here, right? And what does that give us? That gives us I times the principal argument of z, right? Which is exactly the same thing we had before, right? Which is so what we call the, right? And this, right? And right, if we go, right, this, you see that the argument has to be between negative pi and positive pi. Yeah, Kai.
Why do we get, maybe I'm this is something small, why do we get I times the principal argument?
Yeah, so just think about it, right? This thing here is, right, like, let me just write it as r e I theta, right, where theta ranges between 0 and the argument of z, right? So when we integrate this thing, we're going to get I r e I theta d theta, and then on the bottom we get this r, right, between 0 and the argument, right? So you just get I times the argument.
Thank you.
Okay. So yeah, so this is Stein's way of doing it. I think the advantage here is that, well, what's the advantage? Actually, let me take that back. I'm not going to say anything about it. Okay. Yeah, so let me think. What do I want to do next? Okay, so okay, so let me just make one remark, which is that right, if you're talking about the principal log, right, for a fixed branch of the log, it's not necessarily true that log of a product equals the sum of the logs. Okay, right, and the reason is, of course, that right. So Stein gives us an example. He says, well, look, if we take z1 to be e to the 2 pi I over 3, right? So right, we take 2 pi I over 3. Right, and we look at the sum, right? Then then the log of z1 is 2 pi I over 3, and if I take 2 copies of that, right, log of z1 also 2 pi I over 3, but the log of z1 times z2 right, is negative 2 pi over 3, right? Because we use the principal argument, right? So you get negative 2 pi over 3. Right. So that, so the formula doesn't quite hold, right? But if you consider the log to be a multiple valued function, then the formula does hold. Okay. So log z1 z2 equals log z1 plus log z2 in a particular sense, in the sense that both sides yield the same infinite set of numbers. Okay, so like, so here's an example, right? Like, if I write log of e times 1 equals log of e plus log of 1, what I mean by that is that, well, log of e is natural log of e plus I times the principal argument plus integral multiples of 2 pi. Right? So 2 pi z. Right. So that's log of e, and log of 1 is going to be natural log of 1 plus, again, the same thing, right? So, right, and natural log of 1 is equal to 0, right? And you see that when you add this log of 1 onto this, add this set onto this set doesn't change, right? Because you're just adding integral multiples of 2 pi I. Right, and we already have all integral multiples of 2 pi I here, right? So adding this thing onto that, as a set of just if we look at all possible sums here, this set doesn't change, right? And so it's in that sense that this thing holds. Okay. Okay. So let me see if I can do the last part here on complex powers. Okay, so complex powers. Okay, so back in calculus, like how do you define some number to some power? Did anybody remember? How do you define, like, when you're a child, right? You're told how to define things like this, but what about like 3 to the pi or something like that? How do you define a complex? How do you find an irrational power? Yeah.
You can, for the reals, we can take like the supremum of a to the q for all rationals less than or equal to b. Is that what you're looking for?
That's not what I'm looking for. It's true. That will work. That will work. That's a perfectly good answer. Oh, I know. This is actually how, I don't know if you guys saw this back in calculus, but this is actually how you define it rather than using supremums. You use the exponential function, right? So you first have to get the exponential function, right? And then and the logarithm function, right? And then you define it like this. So back in calculus, we defined, right, for A and B, when A was positive and B was any number. Okay, so we'll use the same thing to define complex exponentiation. So for z and a in the complex numbers where z is non-zero, we define z to the a as e to the a log z. Okay, and this log here is the multiple valued function. Okay, so what I mean by that, what I mean is that you know, log z, remember, is natural log of this real number plus I times the argument, right? And remember, the argument was a collection of numbers, right? It was the original argument plus multiples of 2 pi 2n pi. Right? So what is this z to the a? Z to the a means e to the a times that, right? E to the a times natural log z plus I arg z plus 2n pi. Okay. So for example, what do I mean by 1 to the I? Right? 1 to the I, by definition, is e to the I log 1, right? But that's e to the I natural log of 1, natural log of 1, plus the principal argument of 1, which is 0, plus 2n pi, right? And this is 0 also. But yeah, that's right. Okay, so what's that? That's going to be e to the 2n pi I.
What happened to the argument of c?
I'm sorry?
What happened to the argument? Isn't it the argument of 1?
The argument of 1 is 0.
Oh, okay.
Yeah, the argument of 1 is 0. And so we get this. Let me put up another example. Okay.
So we still have to know that e to the I times some real number is equal to cosine. Like to establish that this is well defined, we still have to know that e to the I theta is cosine theta plus I sine theta, right?
Yeah, yeah.
Okay.
Yes, yes. Okay. Sorry. Let me put up another example. Okay. If we think about z to the 1/2, well, that's e to the 1/2 log z, right? Which is e to the 1/2 natural log of the modulus, right? Plus I times the argument of z, plus 2 pi n I, right, for some integer k, for some integer n. Sorry. Right. That's the same thing as that's the same thing as. So I'm just going to use this part to take this is just the positive real square root, right? So it's a positive real square root times e to the I argument z plus 2 pi n everything over 2. right? Which is the same thing as plus or minus z to the 1/2 e to the argument of z over 2. Yeah, so these are, so in this case you see that there's only two possible values, right? So the the square root function is just a 2-valued function. Okay, let me stop there before I go too long. Okay, we'll continue with this the next time.